representing solar neighborhood conditions, so G0 of 1.7. And what you can see here is that most of the mass in the ISM assembles in the cold phase. So this would here be the cold neutral medium. Here is molecular medium, and or in the warm neutral and warm ionized medium, and also in the thermally unstable regime. In between, there's quite a lot of mass, which is actually in agreement with observations there. For example, a paper by Heiles et al. From 2005 already, where he says that a lot of the gas is found in the thermally unstable regime. And the supernova heated stuff is over here and then cools down slowly. So what I want to say with this is that actually a lot of studies in previous years have considered the impact of ionizing radiation on cold gas only. And however, if you have a realistic ISM, your massive stars are not only surrounded by cold medium, but they live in this multi-phase ISM. And okay, maybe in the very initial phases where the massive star is just born and is still fully embedded in the molecular cloud, it would only the radiation would only interact with this medium. But when the bubble gets more evolved, you've seen before, maybe in this one structure of the bubble I showed, there are lots of holes everywhere, and it's not a perfectly nice shell. So that means that also quite a lot of the ionizing radiation is interacting with gas which is already warm and possibly even ionized. And so we studied in this paper in 2018 what happens with regards to the respective momentum input of stellar winds and ionizing radiation when you consider these different environments. And so we looked in particular at this cold neutral medium and warm ionized medium, and we also did many in between. And so just to set the parameters here more specifically, there's a question. Shall I answer the questions now, or do you want me to answer that?
Go ahead, Roman.
Yeah, hi, Steffi. So hi. In your previous slide, when you were showing this distribution of phases, I was kind of trying to understand I mean, the previous one, yeah, this one, right? Sort of the porosity of interstellar medium. You know, I'm used to thinking that in ISM you are dominated by volume, by the hot sort of medium. But so is this not happening here because you're talking about this particular star forming region, which is
this is mass weighted? Maybe that's why. So you're confused why it's here. Yeah.
Okay,
I think that probably explains it.
How would it look if you would do this volume
weighted? Yeah, most of the volume is here in the warm and hot phases.
Okay, okay, great.
And it depends a little bit on the model, and also actually if you include the volume of the hot phase, it depends what exact scale height you're looking at. Right, because the more and more you go above the disk, the more you become dominated, of course, by the hot gas. But also in the disk midplane, we find that more than 50% of the volume needs to be filled with hot gas if you want to drive a galactic fountain flow by supernovae. So that is the general fraction of the hot gas near the midplane is usually more than 50%.
Okay, so these diagrams and all the simulations that you have been showing are sort of done on a galactic scale, so it's like
I will show this in 1 minute. Yes.
Okay, great. Yes,
yeah, I will show the Silk simulations. Okay. So what I just wanted to get at before is that basically it is not enough to just consider the cold medium and say, okay, this gives me the full picture of the relative impact of stellar winds and ionizing radiation, because actually we can understand it even theoretically if we consider the relative impact of momentum, relative input of momentum from wind and ionizing radiation, then it would depend on the environment with which the star interacts. And the reason is that if you are already warm and ionized, then of course the ionizing radiation couples really very little, because all it does is that it keeps the gas from recombining, and there's no new gas which is becoming ionized. And so in this case, the wind, which is actually just producing momentum and or inputting momentum, and this momentum is conserved, would start to dominate over the radiation in terms of shaping the surrounding interstellar medium. So that's actually what I just wanted to point out here, that it's very important to consider both effects if you have a multi-phase ISM. Okay. And so now I'm basically coming to the larger scale models. As we already have seen now in this phase diagram, there's also a third phase, namely the hot phase, which is generally created by supernova explosions. And yeah, so for this, basically, there's the old model by McKee and Ostracker. Roman, you have another question, or the hand is still up? Ah, okay, because it's okay. Sorry, I wasn't looking. Okay, so yeah, so there's the old picture by McKee and Ostracker of the three-phase ISM, which based on Cox and Smith also, we are basically introducing that the hot medium is produced by supernovae. And then I also wanted to point out the later models now by Inotsuka et al., who say that maybe molecular cloud formation is dominated by the multiple compressions, for example, in supernova shocks so basically sweeping up the more diffuse atomic medium and then compressing it to form molecular clouds. And this is actually what we see is happening in our simulations. And so the simulations I'm talking about are the ones which we are doing within the SILK project. So SILK stands for Simulating the Life Cycle of Molecular Clouds. And we first simulated the logo. This was a major thing we did. And after that, everything was easy. No, I'm joking. So and we, over the years, included a lot of physics, and actually starting from the paper from 2015, where we only had supernova driving, and we investigated what is the impact of the relative positioning of the supernovae with regards to the dense gas. From then on, we improved the model and included star formation and stellar feedback. And in particular, what we are doing here is that we are forming basically cluster sync particles, and within these cluster sinks, we follow each individual massive star. So we say for every chunk of 120 solar masses of gas that is accreted, we randomly sample one massive star from the IMF. The 120 comes from when you integrate over the IMF, and you consider then statistically how many massive stars would you form. You get actually one. And so then we sample the mass of this massive star, and then we follow the individual stellar track. Currently, we are using the Geneva tracks for this. But we also have new stellar evolution tracks from Humboldt Fellow I'm working with, Dorothea Schisi, and it's based on the Bonn Cologne. It's based on the Bonn tracks from Norbert Langer. Okay, so and then each of these massive stars has a certain output of ionizing radiation and produces a stellar wind, and also explodes as a supernova. So that means we have realistic delay time distributions for the supernova. So each star has its own lifetime, etc. And so these are run on SuperMUC. That's the cluster. And here's one example for the simulation. So what you can see here is the box we are using. So we have a stratified box. It has a 500 parsec in X and Y direction. And in the vertical direction, we include an external gravitational potential, which is representing the dark matter and the old stars present in the solar neighborhood in this case. And we set up the gas initially as an isothermal sheet, basically, and then we stir it a little bit, because otherwise everything collapses and then you get a starburst. So you need to make it a bit turbulent in the beginning. And then we see how the ISM is evolving. So you can see here a lot of star clusters are forming, and this is a slice of temperature. So you can see there's cold gas, but also warm and hot gas. And in these simulations, we include a chemistry network, which is quite simple, but it allows us to follow the different phases of hydrogen, so molecular, atomic, and ionized hydrogen. And also we form CO. actually in the simulations where you form these sinks and cluster sink particles, the size is not to scale. Yeah, it's just to show basically to give an impression how massive the clusters are. So, but they are not actually to scale plotted here. So anyway, so if we include sink particles in clusters, then a lot of the molecular gas is actually eaten up by these. And so these larger scale simulations are not very well suited for studying the molecular gas and maybe also the synthetic observations or compare with observations what we would get here. For atomic hydrogen might still be okay, but also that you will see later is probably is not super good represented. So we are later on zooming in. That's what I will show you next. And in these simulations, we also include cosmic rays. What we did here is that for each supernova, we inject a 10% fraction in the form of cosmic rays. And the cosmic rays are transported following an anisotropic advection diffusion scheme. And yeah, is there a question?
Yeah, I have another question about simulations, and maybe you'll cover it. So first of all, do you include the shear motion in the galactic plane?
No, in these simulations we don't. That's true. The reason is that for the solar neighborhood, actually on the time scales we look, okay, this simulation now ran for a very long time, but usually we analyzed 100 megayears or so. For the cosmic ray runs, we need to go to longer time scales because the gradient takes some time to establish. But on a 100 megayear time scale, there's very little impact of shear in the solar neighborhood conditions. That's why we neglected it in the beginning.
And do you include magnetic fields here?
Yes.
Okay, and what about radiation treatment or thermodynamics treatment? Do you have like direct radiation transfer in the simulations, or you? Oh, okay. So you don't need to do this kind of equation of state transitions at certain density and so on. You're just doing everything directly.
Yeah, I missed saying that completely, and thank you for asking. Actually, so we are using here our new radiative transfer scheme called tree ray. And I will explain a little bit later because so tree ray does two things. For each cell in the volume, it calculates the local shielding from different directions. We use usually 12 or 48 directions in order to be able to protect the molecules from the diffuse interstellar radiation field, which is dissociating them. And if you don't include the shielding, you actually get the molecular gas fraction really wrong by orders of magnitude. I tested it. So that is one thing tree ray is doing. And the other thing it is doing is that we are doing direct radiative transfer via a backwards ray tracing scheme. So again, for these 12 or 48 rays, nowadays we use 48. In the early simulations we used 12 because the code was slower back then. So along each of these rays we are basically calculating the radiative transfer. We are solving the radiative transfer equations in a backward manner. So basically from anywhere in the grid towards the particular cell I'm considering at the moment. So that's what we do. And the paper is currently under review, and we got a really positive report. So I hope that we will put it on arXiv very soon.
Okay, thanks.
Can I ask you something?
Yeah, sure.
So, I mean, I have also just kind of looking at the movie, it has some impression that when you have a very strong burst, actually it comes with a very large fraction of the cold gas at high altitude. Is that, do you understand why is that?
Yeah, so actually there are two ways to get cold gas at higher altitude. So one is you kick it out directly from the galactic disk. And then we also, in some cases, find that some cold gas and molecular gas sometimes is forming even in the outflow.
Yeah, but so, that formation kind of comes with the burst. I just wonder why that's the case. Yeah. Yeah.
Okay, maybe I.
Now we have a bunch of the cold gas here with this strong burst. Just kind of naively, when you form the large number of massive stars, the radiation field gets stronger, then it will give a much stronger radiation field.
So these bursts you see are usually several supernovae which explode from a similar same cluster. So because consider these timescales are very long, so and then when you have supernova feedback and the supernova shock runs over a structured medium, the dense gas would be compressed and can basically therefore be compressed and cool down. On the other hand, of course, there will also be some heating. So the two processes are fighting against each other to some extent. And due to the supernova bursts, dense material can also be kicked out from the galactic midplane.
I mean, I guess Changu is saying, if you look at the bottom half of this, you have all of these cold structures, and this has not been, you know, the supernova blast waves are affecting things on the other side where you see the hot gas. I think maybe the question was whether it's a radiative transfer effect.
No, I don't think so. I mean, okay, now I don't know. Sometimes the stuff is falling back down, you know, and in the process of that, it's also cooling down. So
yeah, that's kind of the impression is this kind of the sudden appearance of this cold gas at very high altitude comes with a very strong burst. So that is something that I don't really quite understand. So I just wonder you have some understanding on this. Yeah.
I don't.
No, let me interrupt for a second. I see we have a couple of other questions. Let's do those quickly, and then I want to make sure we give Steffi enough time to actually get through other stuff by 12. So,
yeah, sorry.
I'm happy to discuss it later. Yeah.
Can I ask a quick question?
It's quick, yeah.
So I was just going to ask, how are you doing the radiative transfer? Is this gray flux limited diffusion, or is this a full?
No, it's a radiative transfer scheme, really. So we are doing backward ray tracing. I'm happy to show later on some slides in the discussion if you're interested.
Okay.
Xiao?
Quick question, the cosmic ray, do they contribute to ionization?
No, that's really missing at the moment. Yes, they should do.
Okay, thanks.
Okay, so let me zoom in because actually I wanted to show you some of the zoom in calculations. So what we do is that we find molecular clouds which are about to form on the larger scales. And then we basically select these regions and say, okay, this is a region of interest. So we will allow the code to adaptively refine higher and higher in this area. So this is what we call the Silk zoom. And basically it's just showing that we go down and down in scale, and we actually go down to scales of 0.1 parsec. And so this is a volume rendering of one of the simulations with magnetic fields and stellar feedback, now on very small scales. And so we are doing this not by cutting off the large scale environment, but we keep the large scale environment and just really allow the adaptive mesh refinement to zoom in. But if there are like inflows from the larger scale or shock waves running through or whatnot, then we still consider these. So now I show you a few projections of the 3D simulations, which, so here, for example, for 2 molecular clouds. So here you can see the structure in CO. This is scaled by a factor of 100 in order to be able to use the same color bar. Yeah, what you can see immediately is that so what an observer would find from this cloud looks rather filamentary and also quite well. There are different filaments basically which seem to be not connected. However, if you were to observe molecular hydrogen, you would see that all of this is part of the same connected structure, which basically the individual dense filamentary parts are connected by lower density molecular hydrogen and also atomic hydrogen, which is enveloping the whole thing. So this connects to what I showed you in the very beginning in the introduction, that you have this kind of onion-like structure and only parts of it are observable. And if you now try to understand how the molecular clouds really form as a function of time, I show you here the molecular hydrogen and atomic hydrogen fraction as a function of time. And so you can, so this is from time 0 is from when we allow the code to adaptively refine. So basically we start at a time when most of the gas is in the atomic phase, because we want to really follow the molecular gas formation in more detail. And so you can see that it takes a while in this phase, and then the material becomes dense enough such that molecular gas formation sets in. And so then the molecular gas fraction increases quickly while the atomic gas fraction decreases. So if you compare the formation timescales with equilibrium models, where the equilibrium rule of thumb says that molecular hydrogen should form on a timescale which is given by 1 gigayear over the typical number density, then we find that we form molecular hydrogen actually quite a lot faster, so maybe up to a factor of 10 or even more sometimes. And this is really in line with these chemodynamical models, for example, by Simon Glover, showing that you get an enhanced molecular gas formation in turbulent environments. We also have the imprint of turbulent mixing, because molecular hydrogen is present at very low densities. So this is just a slice showing the molecular hydrogen fraction larger than 50% in individual cells. And the other contours show you density thresholds, 30, 100, and 300 particles per cubic centimeter. And so given the time scale we have here, so this is just a couple of mega years, right? So 1 gigayear over 100 would basically give you a 10 megayear timescale for the formation of molecular hydrogen, but already on a few megayear timescale, we are forming a molecular hydrogen way more extended than just in the dark green contours. So it seems to be forming in the densest regions, and then there's some mixing going on. If you look at the movie, actually, you see that sometimes you're sloshing around. It basically almost looks like tidal tails, which is distributing the molecular gas everywhere throughout. So you can expect it to be present in gas which has a lower density than what you would get if you just consider equilibrium models. That's the takeaway message here. Let me skip this. Also, we find in terms of required resolution that we really need to go to very high resolution in order to get converged molecular gas fractions. So again, this is for 2 molecular clouds, and this is showing the fraction of gas in H2 and CO. And what we did here is that we run exactly the same simulation and allow the code to refine to different maximum refinement levels. So in the case here of the Cyan line, 3.89 parsec, so basically that's the original silk grid. And so here there's no additional adaptive refinement. Then here we allow to refine to 1 parsec, here to 0.5 parsec and so on. And we always start from exactly the same initial condition such that we get a comparable result. And what you can see is that basically the finer and finer your resolution is, the more quickly the molecules form. And also you end up with slightly more molecules towards the end of the simulation, just because the denser structures which you resolve at high resolution lead to the better shielding of the molecules from the interstellar radiation field, and there they survive better, and so therefore you end up with just more molecular gas. So I think it's really necessary to go to like 0.1 parsec or so. The thing is that when you afterwards do synthetic observations of these clouds, there is a difference. If you have more molecules, of course, the synthetic observation will also look different than if you don't have them. And I think this is a serious problem with which we simulators have to consider, because the observers, even though they might have a large beam, don't have this problem, because of course nature is basically infinitely resolved, or at least to the molecular level, and so all the molecules which are there are emitting no matter what kind of beam you put there. But in our case, only the molecules are emitting which are actually there in the first place. So this is an important takeaway message. We can also understand why this is the case. And in the beginning I said, okay, for forming H2 or CO, you need high visual extinction. And what I plot here is for the different simulations, 1 parsec going down to 0.12 parsec maximum resolution. I plot the 3D visual extinction in this case as a function of density, but it doesn't matter so much actually what's on the x-axis. What matters is that you see here a visual extinction of 1. That's the black line. And as you go to higher and higher resolution, you just have more and more cells which are where you actually resolve the high densities and which are actually also then sitting at a higher visual extinction. And so these cells are just absent at 1 parsec resolution, or actually a lot of them are just not there. And therefore we form fewer molecules at lower resolution. And it's also starts to become really stochastic here, what is happening. So in this case, I want to point out that this is really the 3D visual extinction. So this is the result of our radiative transfer calculation, where with using tree-ray for each cell in the computational domain, we basically look around us for each cell and calculate the column density along each of these directions, and then form a geometrical mean. We can use a geometrical mean because it's a Hill pixelation of the sphere which we are using. So and the 3D visual extinction is different than the projected one. I will get back to this. So now, actually, how am I doing on time? Not very well. Can you tell me, are you more interested in the synthetic observations, or do you want to see the feedback stuff? Because with the questions now, I think I don't have time to show everything. So, okay, maybe I just continue and then we'll see. Okay, so these simulations we then on the 0.1 parsec scale, we also study the star formation and feedback here. And so what you can see here, I replaced the molecular, the CO with ionized hydrogen. So you can see quite nicely the H2 regions, which are expanding around the young stars. And I think there was one important thing which I wanted to show, which is this one. Coming back to our 2-dimensional density PDF, again, this is a mass-weighted PDF. If we compare the same zoom-in run with and without feedback, then you can see that without feedback, well, it looks like this. It basically follows the equilibrium curve for the interstellar radiation field we set and the solar metallicity. When we have feedback, in addition, then there is this horizontal branch forming at around 8,000 Kelvin or so. This is the H2 regions which are showing up, and the star symbols actually show you where the massive stars are sitting, which are producing ionizing radiation. Not all of the zinc particles here have massive stars. There are also a few which are still, they also could be accreting, but there's some which have not so much mass and which just have not yet formed any massive stars. And so what I think what is most interesting here is that there is really a lot of gas in the thermally unstable regime. And this is mostly gas which is at the borders of the H2 region and basically PDR gas, which is starting to cool down. And if we look here at the movie, so you can see that once the feedback sets in, there is a lot of gas here at the horizontal branch in the H2 regions and starting to cool down. And what happened here at the very end is that my first supernova exploded in the zoom-in simulation. And that's why this very hot gas starts to form. And this finger here also is a remnant of this supernova explosion. Okay, now let me continue because I don't have so much time. But I think one nice thing I want to show you is the following. We studied on the large scales very often for how long the star clusters accrete, or the zinc clusters basically. And so what I plot here is the time from the formation of the zinc until it stops accreting, either due to feedback or due to the end of the simulation basically. So in the case where you have no feedback, the blue points, there is just a variation here in the accretion timescale because some things form later than others. So there is nothing to stop the accretion really without feedback. Okay, so there is some distribution here. Now in the runs with only supernova feedback, there is a particular timescale which is setting the accretion time. namely that's the time at which the first supernova in the cluster explodes. So that's a few mega years for these stellar evolution models. Usually after 3 mega years, you have the first supernova, because the most massive star would explode after a few mega years. And so then suddenly the accretion is shut off. So you get this very peculiar shape here. Now, if we include also stellar wind feedback, for example, then there is a dependency on the cluster mass, because the more massive clusters have higher number of massive stars, and therefore also output more momentum and in the form of stellar winds. And this is basically, if you have more massive stars and more feedback, you can more quickly stop the accretion and further growth of the clusters. And here we just played with the parameters, but in principle, you can see that you get very different distribution from what we had before. And now comparing this to the small scales, we can see, because I was always wondering if this would actually hold if we go to the zoom-ins on the 0.1 parsec scale. And the interesting thing is that it actually does. We also ran the zoom-ins without feedback. So the empty circles here show the result of the no feedback run. And this is exactly this branch, which we also found on the large scale. However, in the runs with feedback, we also start to trail off down towards lower and lower accretion timescales as we have more massive zinc particles. And these over here are still accreting and have not yet formed a massive star. So this is a population which is absent in this plot. Okay, so this just shows you that there is a nice connection between the small scale simulations and the large scale simulations, and that we can actually kind of trust the output from the large scale simulations in this context. And so now I want to use the rest of the time to talk a little bit about this 2D, 3D difference. And in terms of the visual extinction. And so actually I found this, this picture here, which is used for preventing the corona disease to spread. So you can see this is so-called Swiss cheese model. I also didn't know this before. So basically, in order to prevent this lady from being infected, you would have to do many things, one after the other, right? And the Swiss cheese model says, okay, maybe one particular measure doesn't stop all of the virus, but only a fraction of it. But if you do all of it, you have a good chance of basically surviving. Now, basically, if we look at our 2D projected clouds, then this is what we see. So we would see the projection here of this. But if we are in 3D, then we have a Swiss cheese. We are in the middle of the Swiss cheese. So we look around in different directions, and each of the directions, maybe some of them manage to actually give some UV radiation to the particular cell we are interested in. And so for this reason, we generally find that the 3D visual extinction, which are the black lines here for the two clouds, is much smaller than the 2D visual extinction, which are the red lines. And here we have 3 lines each because of the 3 different line of sights we consider. So you can clearly see, sorry?
Could you just say what, I mean, are you defining this based on like the log of the radiation field strength compared to the ambient, or how are you defining the 3D?
So this is really, we calculate the column density along each line of sight in tree array.
Sure.
So here is basically
what is the nature of the averaging? So you calculate that, but you use that to calculate the radiation field, and then do you say that?
No, there's the exponential involved, right?
Okay, so it's basically the log. You translate that to the effective.
Yeah, so the averaging is done for the visual extinction. Yeah, I think so.
I mean, I think that I guess we have defined it using what is the radiation field. If you take that observed radiation field and you compare it to the ambient radiation field, then then that, because it's attenuated differently in different directions.
Exactly, it's attenuated differently in different directions. Yes. And this attenuation we average. Does this answer the question?
We could talk later.
Okay, there are two ways to do it because of the exponential which is involved, and yeah, I think actually we do it in the same way, but maybe I was incoherent now. Okay, so the lines I'm showing here are the green lines is the so-called dense gas fraction from Lada, Lombardi, and Alves, who say that the mass in stars seems to scale with the mass in dense gas, which they define as gas with an a K magnitude extinction above 1, and that corresponds to a visual extinction of above 9, I think. And so basically what you can see that is that in the 2D projection, you have way more gas there than in the 3D projection. And we find that in particular, these two clouds here, which look relatively similar actually in 2D, they evolve differently. And that was always a big puzzle for us because they are otherwise very similar. And we find that the one cloud has more well-shielded gas than the other one. And this seemed to be the reason for this discrepancy. I think I'm running out of time. How much time do I have?
Why don't you take another 5 minutes and then we'll have 5 minutes for short questions, and then we can do more follow-up at 1.
Right. Okay. So maybe I show you some of our synthetic observations. What we have worked on is a post-processing pipeline, basically, for our flash data. In particular, we can connect the data with, for example, RadMC3D or the Polaris code. This is rendering done by Stefan Reisel, where we had the height-et-al simulation put into Polaris. And so in this way, we can now construct synthetic observations from our models and use these to compare with real observations. And so this is one paper which we recently submitted, actually, with one of my master students, Elisabeth Borchert, and she calculated 12 CO120 emission maps for different molecular clouds and different lines of sight, and also for different for these simulations with different resolution, which I showed you in the beginning. And yeah, so first of all, let me show you that well, as you probably know, 12CO becomes very quickly optically thick. And what we show here is two contours. So one is basically what we call the observable area. So we set here an intensity threshold of 0.1 Kelvin kilometer per second. It depends, of course, on your instrument and so on, what exact observational threshold you have, sensitivity limit. So we use 0.1 Kelvin kilometer per second. And then we can, in RadMC3D, determine exactly which lines of sight become optically thick, because you can run RadMC3D in a tau mode, it's called. And so from this, we can see that basically a large fraction of the observable area, I would say most of it, is actually optically thick, and only the outskirts here are optically thin. One thing we also did here is that we, for CO, it's a collisionally excited line. So you need to consider collisional partners, and typically only molecular hydrogen is considered as a collisional partner for CO. But previously we have seen that there is coexisting atomic hydrogen, and also there are some electrons and so on, and helium also is always there. And so therefore we also consider here atomic hydrogen and helium as collisional partners. And we find that in particular the atomic hydrogen is important and might raise the intensity of the CO in these outskirts of the molecular clouds. Now, coming back to what I just showed you about this 2D versus 3D extinction, it actually has the following effect, namely it influences the regions which are so-called CO dark. So CO dark gas is molecular hydrogen, which is not traced by CO emission. And so, yeah, people have been trying to understand where CO dark gas is present. And we can look at this in our simulations because we have molecular hydrogen and CO. And so this is a paper by Daniel from 2019, where we can show, for example, here the dark gas fraction as a function of this projected AV, so the basically observed AV. And this is the distribution of pixels. And we find that there are a lot of pixels with a high dark gas fraction at a relatively high visual extinction. So this is 5. Okay, so 1 would be here. So basically, from an observational point of view, you would probably assume that everything above 1 should be traced by CO. But there are many pixels which are not bright in CO. And we were wondering if there is a consistent discrepancy between these pixels and the ones which are actually CO bright. And this is the case. So if we now look at the PDF of the 3D visual extinction, which is the one which is actually determining whether the molecules can survive or not, then you find that the CO dark pixels have very narrow distribution in 3D in terms of visual extinction, where basically the highly extincted pixels are absent in 3D, while in 2D, you would see this distribution, which actually has these highly attenuated pixels. And these are then CO bright. And so therefore, this difference between 2D and 3D structure is very important. So this is the last thing I wanted to point out. And I think from that, I will jump to my conclusions. And I'm very happy to show you more things later. I showed you that the relative impact of wind and ionizing radiation depends on the environment. And I hope that I convinced you that substructure really matters for these molecular clouds. The substructure is actually inherited from the warm ISM, because we find very similar clouds which have different substructure. And well, since we don't set it up by hand, but we let the cloud form from the diffuse ISM, basically the cloud structure is already imprinted. We can also see that magnetic fields change the substructure. I didn't have time to show this, but magnetic clouds are more fluffy. They have more extended envelopes. And yeah, then I showed you that the volume, which is basically PDR, so which has ionization degree between 0 and 1, can be large, and there's a lot of gas which is pushed into the thermally unstable regime due to stellar feedback. And we also saw that the CO dark gas fraction depends on the cloud substructure and state of the cloud. Okay, thank you.
Thanks very much. That was great. All sorts of loads of interesting stuff in there. I'd like to ask, I think this is Eve's question, but in my way of understanding what about this 2D versus 3D. So I think it's so if I'm a point in the cloud, then even if 90% of my sky area is well shielded, but there's one clear line of sight to a massive star, then it's not quite as bad as being totally unshielded, but almost. Exactly. So the question then is that how you're computing it? You really care about what's the radiation field relative to what it would have been if there were no shielding, rather than averaging over just the attenuations.
I think I was confused about this expression relative to what it would have been, but of course that's the right way to phrase it, because we have an interstellar radiation field which is uniform and set by hand, so to say. So here we use the solar neighborhood interstellar radiation field, and sure, yes, we check how much this radiation field is attenuated in these different directions, and then in the end we know how much radiation is how much damaging radiation, so to say, is coming through to the cell. So this is what we're doing here.
I guess just a purely technical, you can compute what is the radiation field, the averaged over solid angle. You actually compute the radiation field, you divide by what the radiation field would have been, and you take the log, and that is then that is e to the minus, that's tau, right? So that's one way of defining it. Is that the definition, or did you do some?
Yeah,
kind
we just don't do it with really the radiation field. So that's why I was hesitant in the beginning. So what we do is that we just calculate the local visual extinction in all the different directions, and that involves already e to the minus nh, so to say, and then we average that. Yes.
So you're taking an average of e to the minus tau.
Yes.
And then you.
That's it. And then
you define that average as e to the minus tau effective.
We're averaging AV. I'm pretty sure about that.
Okay, so yeah, I'm not sure it gives the same result, but
yeah, that's,
anyway,
that's actually quite different.
Let's maybe that's
if
something
you want, I can check it
later.
because yeah.
Sukanya.
Is there any dependence on the metallicity for the CO dark gas?
Yeah, there should be, but we haven't calculated it. So the metallicity directly impacts how much molecular gas you would form in two ways. So of course, lower metallicity means lower carbon and oxygen, right? So that scales linearly with the metallicity, and then lower metallicity also usually means lower dust. So we have a very simple dust model. We use a constant dust to gas ratio, and we scale it linearly with the metallicity, which I think is okay down to metallicities of 0.1 or so solar. And so the dust shielding, before there are any molecules formed, the dust shielding is the most important shield. Afterwards, when you have molecular hydrogen already, it likes to self-shield. But before you have any molecular hydrogen, you need to form it in the first place. You need the dust shielding, and if there's little dust, it means you need much higher columns. You need to integrate over a longer line of sight, so to say, in order to get the same shielding.
Yeah, and you're calculating the temperature everywhere, right? Because you're doing. So why do you need rad-MC and these other post-processing things?
So we are actually calculating dust and gas temperature separately, we need rad-MC in order to do the radiative transfer, because what I showed you here was that a lot of the emission becomes optically thick, and so in order to then get really the image, you really need to do the radiative transfer. Otherwise, if you would just integrate along the line of sight the emission which you would expect in the optically thin limit, you would get too much emission out. You would overpredict what you see.
Okay, so you're not actually doing a full radiative transfer calculation during the.
No, we are doing that, but not. I mean, if you want to have a 2D image, then you still need to do a post-processing step with the radiative transfer tool. I
can.
understand.
I'll ask you later, I think.
Yeah.
Last questions from Xiao.
Yeah, so some sort of studies suggest that cosmic ray can also help the development of the multi-phase of SM. Do you see such effect in your simulations?
So what we see is, for example, that with cosmic rays, the structure of the outflowing gas is very different. So in particular, with cosmic rays, we get more smooth outflowing gas. And so with kind of less substructure, and it's therefore also cooler and than what you have if you do not include cosmic rays. And so this is one of the main effects we saw on the larger scales. Interestingly, the models with cosmic rays are the only ones with which we can, for example, correctly reproduce the expected Lyman alpha line profiles. So if you look at Lyman alpha lines from galaxies, you see that there's an asymmetric shape, and that the emission really goes to zero at the line center. And basically, the Lyman alpha line profiles can be modeled very well with kind of an expanding shell structure. And it seems that due to the smoothness of the outflow with with cosmic rays, we can reproduce it. Otherwise, we can't, because it's too clumpy, the outflow. So this is one of the main impact.
So do they heat?
Yes, effect, but sorry.
I said cosmic ray. Do you consider their heating effect?
Yeah, we can sitting, but in these models we have basically constant cosmic ray ionization rate so far. So we're working on this. Can you hear me? Because it's
yes, yeah. So I mean, so the cosmic ray, do they have feedback? Like, do they drive waves, alpha waves, and they heat the gas?
So in principle, they could heat the gas, but so this is not yet taken into account properly in the chemistry model. So this is a work in progress.
Yeah. Thank you.
Mm-hmm.
Okay, well, thanks very much for a very rich talk on both the methodology and the implications. I encourage people with further questions to join us at 1. But thank you again. And the 1 o'clock conversation will be just on this same Zoom link. So thank you.
Well, thank you very much for having me. I'm happy to discuss now. If you want to have a break, it's fine also.